Hey, Tyrion, what's going on? This music is very energetic. Excuse me. It is Friday night after all. Am I publishing the notebooks? I am, but I'm gonna change up the style. So I am going to make a GitHub and post or push all my notebooks up to that, and then so they'll be publicly available to everybody, all the viewers and stuff. But it's also so that I don't have to I can actually use the functionality of kind of Git, and not really trying to control a version, but to just kind of easily replace files. So I can just push updated notebooks that I say use from stream to stream, instead of having to delete a notebook and then upload the new version and stuff like that. And it'll be interesting. I've never used GitHub before. I went to a Git workshop a few years ago, and I really like the idea. But yeah, so it'll be a learning experience. So kind of what we're doing here is, it's been a thought in my mind that for a long time that Mathematica would be a really good resource, would be a really good way to kind of present or to teach Fourier series. And maybe that thought is correct, maybe it's not, but use Mathematica to control Git. I'm sure it's out there. Emergency, welcome on in. But yeah. Hey, make it work okay. I am a fan of that philosophy. Make it work okay. I wish I could make more of these, but after a day of work and school, I'm whooped. Yeah, well, I guess I'm thankful to only have one of those. I did work a full day today, but it's Friday night, and I guess I chose to do this with my free time. Okay, so this is right now I'm just kind of making an outline. Feel free to ask any questions, or provide any insights you have to teaching Fourier series or about Fourier series and analysis itself. So let me know if the audio levels are good, if the music is too loud or my voice is too quiet. Anyways. Well, thank you very much, Make It Work. I really do appreciate it, and I do put effort into this, and I like it, and I do it for you guys. And yeah, I also have a good time. Good call, Tyrion. Okay, so what does it mean to have a basis? What kind of bases? Or what kind of a basis? So, e.g. ortho normal or not. Explains how this also corresponds to functions. And then make the equivalence between the, well, finite and discrete. Finite and discrete version of a vector to the function vector. Fourier transform of B's. Here you go. I'll do it right now. Bees. Bees like to fly, so we'll take the Fourier transform of bees as they fly through the air and represent it in their momentum. Or transform doesn't take a list. There you go. The Fourier transform of bees. Look at that. Of course, you know, this is actually assuming bees is constant. But what if we do that? Look at that. It doesn't return anything because it doesn't know what bees is. We'll say, assuming bees is constant. There you go. So like do some emergency temporal shift, do some signal analysis on the on some bees. I imagine it would peak in the low frequencies. We'll make another section for this. We'll say other stuff. So what kind of basis explain? Bases. Well then, what is a Fourier representation? Or not section, subsection. Then we'll talk about Fourier series, and then in the next section we'll talk about Fourier transforms. Transform? Series? Transform? Is series... Here's a question for y'all. Is series singular or plural? I think we need to have a poll. Plural. Alright, chat. It's up to you. It's up to you to decide the future of this word. So what is a Fourier representation? Well, not up here. Bases of orthogonal functions. It's like sand, or moose, or fish. Oh, two. Okay. I guess maybe there should be a both option. Here, I'm going to close the poll, and then I will add a both option. Okay. Tyrion coming in hot with the both. So here we would say, talk about, show how the standard trig functions are orthogonal at the least. I forget if they are normal. So make it work. How about set? A plural or singular? I'm not sure I understand. A set of 0 elements, 1 or many. Both. I still don't understand. Am I missing something? Are we talking about sets or classes? Series is one series or multiple series. Yes, so that would be both, according to that logic. A series or those series. But see, those series is like that. I don't know, that feels weird to me, but probably just because I've never said the phrase those series before. Granted, the course I took in my undergrad math program was a course I took, kind of an intro to analysis, was limits and infinite series. So I guess in that sense, I mean, you know, if you're assuming consistency in the title and the things listed in the title, and they're both plural, then limits sets the precedent of talking about a plural thing, and then going on to the next item in the list would say that series is also plural. So make it work. Yeah, just think about the word set. Sure, they could be empty, but it could also be one or many. I mean, I think maybe I'm starting to pick up on what you're saying, but I'm failing to get a bijection from the thought that maybe you're having and what I'm picturing in my head, or the meaning of what I have in my head. So for Fourier series, basic theorems and conditions on Fourier series. About, well, basic / fundamental theorems and conditions on Fourier series. About convergence of series, and say something along the lines of this function has the Fourier series as opposed to having a, well, yeah, Sound test. We're gonna lower the music a little bit. What if I go like that? I like that. Okay. Okay, we're back. There may be an in and out thing. So then, along with this, maybe get into, say, pointwise convergence of a series of functions versus the maybe required, the what's it called? Absolute convergence. Silent stream. Oh, sorry about that. Could do a silent stream, have it just be purely visual. Just visual, you just get to look at the code. You don't even hear my clicky clacks. Nope. Okay, so then bring the previous discussion back to the transition between discrete vectors and quote unquote continuous vectors. Up here, show still components as well, plot components as a vector. Let's see, with the normal, explain how this corresponds to functions and make the equivalence between finite and discrete version to the function vector. Talk about the distribution of component values. Make the corollary to derivatives. Make the corollary to derivatives being so emergency. You need a pretty graph at the bottom to look at. We do need a pretty graph to look at. Let's see. Let's have a pretty graph to look at. We'll put a pretty graph right here. We'll say, what's a good Fourier related graph? We'll say animate, and then graphics row, and then plot and say oh yeah, sure, why not? T from, oh, I don't know. Well, yeah. Negative pi to pi. And then we'll say epilogue. And then we give this point size 0.03. And we make it red. All points must be red. And we say point at t exp of t. Then we close the epilogue. And then that's our point. And then we also say, more or less, plot the Fourier transform of the exponential function, whose variable is t, and we want to go to omega. But then, of course, this gives us a complex valued function. What? Hold on, fam. Why does this not evaluate? Does the Fourier what? Am I missing something? That the Fourier transform of the exponential function just like doesn't exist? Yeah, there's 48 parameters. Let's see, Tyrion, are you using a math physics book as reference? I mean, math physics book, meaning my brain, if that's what you mean. Just going off of my memory and my own thoughts on how to teach and what goes in, like, or my thoughts on how Fourier analysis makes sense to me. A mathematical physics book. Nope, I'm not going off any reference, just kind of putting my own thoughts on paper and seeing what comes out. So if we have this, ignoring the Fourier parameters, which we could change. So 1 over 2 pi, and then if we say f of t is, that's very small for you all. Also very small. And so if this is e to the t, and so we go do, and so we have e to the t plus I omega t. And so we have e to the t plus, or e to the t multiplied by the quantity 1 plus I omega. What's the Fourier transform of that in t? Yeah, that's weird. So I think you can close the poll now. Well, I'm going to leave it up. Well, I'm going to leave it up in case anybody else comes in and they want to provide an answer. It's a good conversation starter type of thing. Well, I guess just to not kind of bog things down, we'll just take the Fourier transform of the normal distribution, which, guess what, is also a normal distribution. And so what does that mean? That means So we can say, hey, look at that. The normal, or the, let's see, Gaussian is the eigenfunction of the Fourier transform operator. Kind of. Well, I mean, not really, actually, because there's that. Unless we say, oh. Aha, there we go. Okay, but anyways, so let's say that's not what we wanted. So let's go over there, and then let's come over here, and we say there's that. Okay, so now we do that, and that goes like that, and then we have a point, and it's going from there, and then we're also going to say I mean, we could. I mean, why not? So we're going to make this a module, and then we're going to say f is the specification of a low-level function. Does t come after? I don't think so. Well. Then we can just make this a function. And then we can say ff is the what ends up to be the Fourier transform of f of t. That needs to be there, that's at that, and that goes over there. And then over here, we say f of t. And then over here, we say ff, because animate is really block under the hood. And so the kind of evaluation of t will go inside this definition. There's that block. Well, the module is on the outside, so. And so we go there. And then we go like that, and then we go like that, and then we go like that. And then we say, okay, where do we want to animate from? We want to animate from t equals negative pi to pi. And we hit enter. Oh, look at that. I don't know what I expected. So let's see. Fourier transform, context, all context. Should be a pair of numbers. That is correct. So basically, let's take out this and do some debugging. And we say f of t and then ff. Because it did not do what I thought it would. There we go. I guess module is more like with in that case. So, emergency temporal shift. What does the ampersand at the end do? That is a good question. So, this gets into, I think something I talked about a little bit on the first stream, but so the ampersand, the inclusion of the ampersand has to do with the existence of this pound sign right there. One second. And so basically what this is saying is that The inclusion of the pound sign is basically a variable without a name. And then the ampersand is saying, okay, everything to the left within the parentheses is a function. And so what this is saying, another way of writing this statement is the usual, say f of t equals our Gaussian function. These are equivalent. False. Well, yeah. But yeah. So let's see. Let's go back down here. Right. So cell complex FF should be paired numbers. Right. So it's not evaluating FF. And so we do that, and then right, because FF needs to be so if we go over here and we say, okay, force that evaluation to happen first. Well, since we have, well, no, because we can just, well, no. So what we want is this, and then we can go over there, and there's that. But let's remind ourselves exactly the syntax information of the function. So right, the function takes the variable as the first argument, and then kind of the quote-unquote output as the second argument. And so if we go like that, so now FF is a function. Yeah. So we'll say that, and then so this should be right. It doesn't know what f is. Right. I was just doing that to display anyways, but now let's try it. Well, it still doesn't work. It still doesn't like it. Okay, so plot f. So this is just the regular function itself. Oh. Let's make that f of t. Right, it doesn't know what omega is. So there's that. That's why it's not plotting anything, because FF. So that, okay, so FF is now a function, and so we're going to make that, and then we're going to make Chat, why did you let me do this? That doesn't make any sense. Let's get rid of the animation. Okay, so we got rid of the animation because what I was trying to do was make a point travel on two graphs where one of the graphs was the Gaussian function, and then the other graph was the Fourier transform of that Gaussian function, which, due to its properties, is the same graph. The one function is in the time domain, and the other one is in the frequency domain. And so I was trying to basically, I was modeling a point moving in the time domain in the frequency domain, but the animation was kind of moving time along, but that doesn't make any sense, or that doesn't apply to the frequency domain plot of the Fourier transform. So that's what I was trying to do, except that doesn't make any sense. Emergency, I let you do it so you could learn. Fair enough. Fair enough. But anyways. Okay, so let's have this, and then this is our time domain, and then this is our frequency domain. We don't want any of that. Excuse you, that is not a graphics row. Oh no, I see what you're doing. The list as the first argument of graphics row. Look at that. Except now we say axis label is frequency omega. And we say none. And then similarly, we can say time. But we also want each of these image sizes to be, oh, I don't know, 2 inches. And the inclusion of the nested image sizes is always a pain. We want this to be 4 inches. The reason why I have a 72, why is this not working? The reason why I say inches upon the inclusion of this multiplied by 72 is that if we go to the image size documentation, we can see that, where is it? Right here, you can say 72 times kind of our input is di inches before magnification. So basically without that, if we just give it D, then that's the printer points. And so basically what it's telling us is that what is that fraction? Yeah, 72 inches. Or wait, no. Yeah, there's 1 inch for every 72 printer points. And so when we multiply it, we cancel out our 72 printer points. And then with our kind of printer points on the bottom here, and then we get di inches. 72 is a magic number. Magic number bad. Magic number is good. That's why we can have this thing, because we have magic numbers like E. So what are y'all up to tonight? It's a Friday night. And you chose to come see me. Or to hear me, rather. I'm going to take these out. Well, I'm going to take these out. Nested image sizes are weird. Emergency, but magic numbers are supposed to have variables. I must not be on the up and up of what the definition of a magic number is. Isn't a magic number also the name for what is it? Numbers that are equal to the sum of their factors? Their prime factors, maybe? I'm not sure. I forget. But then since we don't want it that big, we're going to say act best ratio 0.25. So emergency says a magic number is a numeric literal, such as 8080 or 8080 or 2048, that is used in the middle of a block of code without explanation. It is considered good practice to avoid magic numbers by assigning the numbers to named constants. Oh, look at that, the poll closed. Named constants and using the named constants instead. I see. 72 is a magic number. Magic number bad. Okay, yes. Now, I think I would agree with you. Yeah, my advisor in school would always work in centimeters. And so I think it was... Well, there's 2.54 centimeters to an inch. And so... and there's 72 printer points per inch. So he would always say something along the lines of, to find the centimeter unit, cm, and so cm is like 72 over 2.54. Is that how that works? 72 printer points per inch, and then 2.54 centimeters per inch. And so you flip those units, and so you have 72 printer points per inch times what am I saying? Inches per centimeter. So you have, right, and then so you have this many printer points per centimeter, and then you would multiply, well, and then you would say, oh, I want this to be 10 centimeters wide. And then it gives you the number of printer points that the image size function actually takes. Okay, but anyways, now we have a graph we can look at if we really want to. But anyways, so let's go back up here. Let's get back to the task at hand. Look at that. Y'all got me off on a tangent. And then made me put stuff where it doesn't belong. Sounds all gonna go down there. But now we can't see the graphs. Well, we're not gonna look at the graphs. You are able to also request songs if that's what you want to do. We also have some other, very few custom commands. I'm open to suggestions. But if you want to check out the custom ones and the standard ones, feel free to check them out there. Never going to give you it. Well, I would say I don't want to get copyright struck, but I doubt the system would notice me. We listen to just the beginning. Is he going to do it? Look at that. So now, if we listen to the rest of the song, because it's a very good song, and then we listen to that, we'll listen to just the beginning, which is arguably the best part. Oh, 1 second. Gotta sneeze. Okay, that's better. Okay, I can't think of exactly any more concepts I want to add to the list right now. So let's just start throwing stuff in here. So let's say, down here, consider the vector in polar, we'll consider a vector in polar coordinates. Well, and we're actually going to take this and then convert this cell to code, and then we're going to make this a comment, and then we're going to say clear vec, and we're going to say vec equals r. What have you done? What have you done? You've rickrolled us. You've rickrolled us all, and it's my fault. We're fine up until the voice. Right there. That's what you get. That's all you get. Okay, so we consider this and say, why are you clearing things before using them? Why am I clearing things before using them is because, say I run this cell. So if I don't include that, then, so I run this cell the first time, and it says, okay, vec is equal to this thing. Or rather, vec of t is equal to that thing. I could put this, in fact, I will do that just to not teach bad habits, but you don't, the Jedi won't tell you that you don't need this colon in most circumstances. But, so I run this cell, and it says, okay, vec of t is now this thing. And if I run it again, then it is not always the case that this new, say if I change this, that this right-hand side, or this possibly new definition, completely overwrites the function. And so as a way to negate those effects, not even mitigate, but negate them, is to always include a clear command before the assignment. And so that way, you are always getting exactly what you think you are. It is very much the case that sometimes, I'm not even sure exactly what triggers it, Mathematica gets confused if you try to overwrite an assignment without clearing the variable first. It kind of mixes the two definitions, and then you get weird stuff. So this is an example. Why include this? Prudent programming, as one of my professors would say. So f of x. So it's not that it could be defined as multiple things, but those multiple things could come together and form one thing that you don't know what it is or what it does. Good question, though. So if we go over here, and then we say, now we can get into our animations. Well, yeah, well, let's make it a manipulate, and then with an animator control type. And we say but we don't want plot, we want parametric plot. We want t to go from 0 to 2 pi. And then, much like always, because we like making, no, that's not what I wanted. 0, 3, and then we make it a red point, and we say point at vec of tp, or rather t prime. So with that, and then we close our parametric plot with our epilogue, and then we go down here and we say tp is our kind of time, our actual time variable. And we say this also goes from 0 to 2 pi. And we go like that, and oh, but we also want this to be an animator. And so it goes around and it's a ton of fun. But then what we can also do is put this into, well, we were split on the pole. So I'll say both. I like both. And so we come up here and we say graphics row. And then we go to the end of that, and we close our list inside the graphics row, just to make sure we don't end up missing that, or to make it easier for ourselves later. And then we also say, okay, list plot vec of t. Let's see, can you rotate the whole manipulate box? Probably. Yes, probably with this. Which we will see in just a hot second. Well, right, because yeah, and so this is our list, and then we have this, and then we have this other graphic, and then we go over here and we close our graphics row, and then we go up into the manipulate, and then so we have that, and then look at that. I can't pause it. What have you done? Pause. Pause, please. I cannot interact with this at all. Okay, well, we'll just delete that. And then go back over here and have a nice little guy. And we go over there. And we say that we want this image size to be bigger. Say, oh, I don't know, 6 inches. 10 inches. There we go. But so what did we do wrong over here on the right? Let's plot vec of TP. But because things are varying, we need to say plot range, specify a constant plot range of 0 to 2, and then a y range of -1 to 1, 2, 1. And then close that, and then we can also say plot style, and then we give it a directive, and we say point size 0.03 and red. And we don't want 0 to 2, we want 0.5 to 2.5. And so, what do we have here? We have the components of, well, let's put these on here. We can say plot label components of the moving, well, of the vector. Components of the vector. Okay, Mathematica, calm down. Let's go like that, and then similarly, just to be consistent, we can also say the vector. What is happening? Wow, it really doesn't like to have plot labels. What happened? So it's choosing set inches to 72. Yeah, you could do that. No, don't do that. So let's see, emergency. Would a little vector be too much to ask? Would a little vector, or have you given up on those? Are you saying kind of arrows to these points over here? Because we can certainly do that. That's not hard. We certainly can. With a good old... Let me get rid of that first. Because, and then we can say, we want some arrow, we want some thickness. Actually, you know what? How about this? Well, we can just do this also. There we go. Arrow from well, we want 2 arrows, so we can say, if we go down here and we say, oh, arrow, well, because we want the arrow to go from the x-axis, so that's 0, but then 1 and 2. Well, I suppose we can really just go here and then to do it a rather kind of lazy way. We take that and then we put this right there. And we let it yell at us. Okay, I need to save this notebook before it crashes and I lose all of this work. So we're going to Alt-CL, and then we're going to copy that and save this. And we're going to put it right there. Yeah. Save, please. Sit. Oh, you're right. You're right. Look at that. Look at you being so smart. Okay, but anyways, okay, now that it's saved, we can do anything we want. Like, look at giant red squares. So if we let that pause and go through its thing. So if we get rid of that and then see what I'm actually trying to do. So yeah, we want an arrow and it goes from 1, 0 to cosine TP and then 2, 0 to, yeah, that is exactly what I want. Except, well, what if we go like that? Fam. Look at that. It still doesn't like us. Why doesn't it like us? Okay, maybe we should just look at the error messages. Coordinate 1 should be a pair of numbers or scalar offset form. 1, 0. Oh, because look at you guys. You're so smart. Lisp levels of Lisp levels of curly brackets. Look at that. I don't know why that's being so slow. Let's take out the plot labels and see what happens. No, don't evaluate. Abort. Abort the computation. Delete that. Yeah, it just really doesn't like plot labels for some reason. I don't think I've ever had that happen before. So yeah, look at that. That's beautiful. And so this plot on the right, okay, emergency, can some sort of timing command diagnose the slowness? Can it diagnose the slowness? No, not that I know of. It could probably work if I rasterized the kind of image before, or when I include the plot labels, but when I was toying around with this a few days ago, I got into a situation where I think Manipulate really did not like messing with rasterized images. But yeah, so look at this cool thing. So 1.0 and 2.0. But yeah, anyways, so, well, also what we can do is, so there's a point there, but we can also, in addition to the epilogue, or in addition to the point, have the actual kind of arrow vector point to the point. And this one's easy. TP. And so each of these vectors corresponds to the x and y coordinate or component of this rotating vector. And this is just something that, I don't know if you guys ever saw it, but this kind of representation of the components of a vector is something that I never saw in school, but I think is very illuminating to when you talk about how functions are, well, kind of graphs of functions are really just this same idea. And then you talk about how continuous functions are vectors themselves. And that's exactly kind of what I want to do here in this notebook. Well, one of the elements. You can also think about sequences, infinite sequences being infinite dimensional vectors. But yeah, I've always really liked this animation here. But yeah, so that's fun. Okay, so that's done. And then we will delete all output, save our notebook, and then run it again. And then we can move on to the next thing. So we did this. We go over here and we say, done. Come on, where is it? There it is. And then, well, it's kind of also same thing. So we can just pause this to see a snapshot at any time. So like right there. I see right there. But yeah. Okay, so I think we can move on. I'll leave that there in case we need to come back to it. So, now moving on to what does it mean to have a basis? And what kind of basis? Orthonormal? Orthogonal? Or not? So, because basically, we want to start out with the very illuminating statement of a vector is an element of a vector space. And also, a vector is a vector. let me say, the key part here is that vectors themselves don't depend on the choice of basis. There are a few properties of vectors that kind of illuminate this fact. Namely, the norm of the vector. So then here we could really talk about, we could also go into basis transformations, which are very, very important. I'm not gonna, well, how corresponds to function make equivalence between, take distribution of component values, make the corollary derivatives. I'm gonna put this, well, we're gonna talk about, we're gonna add a thing in here. And to talk about inner products. What does it mean to have a basis? So a vector is an element of a vector space, and also a vector is in fact a vector. So the key part here is that vectors don't depend on the choice of basis. There are a few properties, da 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 da. So we can, with a choice of basis, we can represent the vector as a, what's it called? A linear sum? Linear superposition? What's the word I'm looking for? Linear combination. There we go. Can we represent the vector as a linear with a choice of basis? We can represent the vector as a linear combination of the basis vectors and, in bold, the appropriate components. Nope, that's not what I want. The appropriate components. Because the choice of basis determines the component representation of the vector. So with the choice of basis, we can represent the vector as a linear combination of the basis vectors. Right. And the appropriate, or with the choice, we can represent linear combination of basis vectors. Period. This linear combination determines the appropriate components because the choice of basis determines the component. That is a very redundant statement. With the choice of basis, we can represent the vector as a linear combination of basis vectors. How about just the choice of basis vectors? The choice of basis determines the component representation of the vector. I will smooth that transition out later. How we doing, chat? Let me turn up the music a little bit. So let's see. Yeah, I like that. Alive. Yeah, fair enough. Tyrion, you still there? Did you fall asleep? So let's see, the choice it right. And so we can kind of comment here. This fact is exactly well, maybe not exactly. So this fact is almost exactly the idea behind the Fourier representation of a function. Okay, so I think we can start visualizing this. So yeah, this is our ideas to implement. We're not going to worry about that part. What does it mean to have a basis? We're also going to come over here, turn on movie mode to kind of brighten things up a little bit. What does it mean to have a basis? And choose a basis. So we can say where's 7? Consider a vector in R2. So then we can say graphics. This can just be a one-liner. Arrow from, say, 0 to 1, 1. And there, that's all we, nope, not red. Well, I don't know what I expected. And so then we can say, well, let's take this, delete that text cell, put this in comments, and then we can ask, what are the components of this vector? But psych, it's a trick question. Psych, it's a trick question. Because we say the above is a trick question because the components depend on the choice of basis. Those comments look out of place. Yes, that's because I would say they probably are out of place, but I'm just kind of trying to get words down on the paper, on the screen right now. because the components depend on the choice of basis. So we can say, so let's choose a basis. Well, let's choose some bases. So if we say have this, and then we now come down here, and we go like that, and we go like that. We can say, okay, give us two. Let's give us the. We can actually move this out of here since we're doing multiple, and then it will apply to all of them. So let's just take the. Let's take. Good job, chat. You're smart. Let's take this and then go from 0, 0 to 1, 0. And look at that. Now we're supersonic racing. And then also on there, let's say text X at the position at there. We can also go like this, and we can say Mm-hmm. 105. But then we can also change these to be bigger and say bold, and we're going to make them size 15. Oops. Then we go to the end. And we paste. But then we can also stipulate. So here's some correctly placed comments for you. Here's the vector in question, and then here's basis vector 1. And we can say basis vector, guess what? 2. There. Then we can say prime basis vector 1. Can you guess what it's going to be? Sonic racing. Actually, because I don't want to do the math. We're going to say pi over 4, and then dot 1, 0, and then And we're going to say x prime. We're going to say y prime. Except now we're going to go over here. Well, actually, and that's like that. So we can get rid of that. But these are also going to be dashed. Well, maybe we won't go the full 4. We'll go 3. Oops. How you doing? You still there? That's not what I wanted. X prime right. This is bad coding, but I don't care. I'm not feeling that song. There we go. Oh, what did I do? Rotation matrix by pi over 3. Yeah, so this one is good. Oh, I needed it. There we go. Could use rotate matrix just as easily. What do you mean? Isn't that what I'm doing? Jeez. There we go. I could have sworn there was a rotate matrix that took 2 arguments. There might be. Nope. And so now, what we can do, space vector 1, basis vector 2, and then prime basis vector 1, prime basis vector 2. So now we can, now that we have some bases, we can find the components of the vector in them. Here, let's do a good old save. So now we can actually, let's go basis n. Well, let's go basis equals the identity matrix. Well, yes. Because Mathematica has kind of a preferential, intrinsic basis. Of course, being up and down and left and right. And then we can say prime basis equals really, I think just that. Does that look right? Negative. Oh, that's not right. And now it's this. There we go. Oh, it's the... which is really just the transpose. That looks right. And I guess just to show, we can say that. So we can say well, and then here we can say the eagle-eyed among you may be asking how can we determine the components of the basis vectors without first choosing a basis. And that's a good question. The components of the prime basis are with respect to the vectors of the regular basis. There's some good stuff. Do I want to go on or not? I'm kind of tired. Let's just do this last thing. Let's just represent this vector, the vector in question, in the different bases. And we can do that with some inner products. We could also represent it in one and then do a basis transformation between them to get it in the other. But that's not what we want to do. Use some Jacobians. Or I might just stop here. I kind of hit a wall. So let's see. Okay, well, so if we have our vector in question, and that is, say, 1, 1. Which we'll put up here, just V. And so now we can say, what are the components of V in, or with respect to basis. Let me close our comment. And we say, okay, well, V, the vector V, and so we use exactly Fourier's trick. Use so in the basis of our kind of this basis, say E1 and E2, the component in E1, how similar our vector is to the x kind of x vector is we take the inner product of it. And so we say, okay, what's that? Or well, we can kind of do it longhand and then show the equivalence. And then likewise, we would say, oh, what's that? But then that is really just V dot, well, basis dot B. I mean, the inner product is commutative. The inner products are commutative. And we say, oh, okay, in this basis, our vector V takes the form 1, 1. And then similarly, we can take this next one. What are the components of V with respect to the prime basis? And likewise. Now, of course, the kind of tricky thing to remember here is that these numbers aren't with respect to the prime basis, but with actually respect to the intrinsic basis. Right? Well, this is really some prime basis 1.v prime basis 1. Well, prime basis k and then k out to length prime basis. Okay, well that's different. Oh, wait. Right, because this representation is intrinsically represented in the intrinsic basis because of how this list structure is defined or represented or interpreted by Mathematica. I mean, yeah, that's what I expected. Yep. That's exactly what I expected. Okay, I think I'm going to call it here. Emergency temporal shift. Thanks for hanging out again, as always, even if you are still there. Hopefully I'm not just talking off into the void, but I really do appreciate it. You know, even if there's just one person here, I'm more than happy to do what I can. You're technically awake, yeah. I'm more than happy to do what I can and hopefully provide at least some modicum of enjoyment. But so, I hope you come back next time, and we will definitely be revisiting this, because it's a thought I've had for a long time, and I want to put it down on paper and hopefully illuminate this subject for others. But so with that, I guess I will sign off for the night. Yeah, no, it's been great having you around. You're giving some life to the Discord and the chat as well. And make me feel like I'm not just totally failing. It might help if I actually stream during the day, but that'll be tomorrow and Sunday. So, I say thank you to all of my one viewer out there. And day stream might be nice, yeah. But yeah. Alright. Don't have too much fun. And have a good night. I'll see you next time.